Good afternoon, everybody. My name is Scott Burleigh. I've been working on DTN for a long time, sort of since the beginning when we started talking about it in 1998. And what I'll be talking about today is an application of the DTN architecture that I think the discussion will echo on a number of the things that have already come up during the presentation so far today. It is about using DTN in space, but it's also very much about using DTN to improve the conditions of people on Earth. It's about terrestrial applications for DTN that are supported from space. So I'll get into that now. There's the backbone of this talk, I guess, is a proposal for infrastructure, a constellation of what are called nanosatellites, very small Earth-orbiting satellites that would use delay-tolerant networking to provide low-cost network access universally across most of the globe. I'll go through an illustration of how that infrastructure would function, and I'll go through some details on what I think the capacity of that infrastructure could be, what the costs of deploying that infrastructure would be, and as a result of those, sort of what the benefit of the infrastructure would be in terms of providing very economical network access. I will then sort of talk a little bit about the application operational latency in that network, and some applications that I think would work just fine despite that latency, which I think kind of motivates development of the infrastructure that I'm talking about. Sort of closing with stepping back a little bit and having a broader perspective on what it is to use a network and what that means, and a little bit on caveats and the outlook for this idea. So the concept I'm working with here is using satellites for universal network access. We all know already that Earth-orbiting satellites can relay radio communications among sites on Earth, which is a great way of providing communication from any point on Earth to any other point on Earth through Earth-orbiting satellites. They have the advantage of being visible from all points on Earth's surface, depending on what the orbit inclination is, and as such, they remove a lot of the geographical and potentially political obstacles from communication. The communication can easily span national boundaries. It can reach into parts of the world where political considerations may be shutting down other kinds of network access. And this is not a new idea. There's plenty of satellites up there now. There are loads of geostationary satellites that are providing communication service to large parts of the planet, Viasat, HughesNet, Intelsat, Inmarsat. And there also are low Earth orbiting, or LEO, constellations that are sort of structurally entirely different, but also are providing service to large swaths of Earth's surface. Things like Globalstar, Iridium, Orbcomm. Teledesic was doing it. It's out of business now, but there's still other constellations that are in business. So is the problem solved then? Because we've got constellations, we've got satellites. What else is the problem? And the problem here is that maintaining internet connections with satellites is absolutely doable, but it's not necessarily easy. With geosynchronous satellites, the satellite is in one place over the same point on Earth's surface at all times, which geosynchronous means. And so you can maintain continuous radio contact with the ground station, between ground stations and customer equipment through that satellite. But those satellites are very expensive, on the order of $300 million or more to manufacture and launch. Each satellite provides communication to a limited part of Earth's surface because it's only visible from a certain part of the surface because it's geostationary. That may be a large part of Earth's surface, but still it is limited. Each one is a single point of failure because they're expensive. You don't have an awful lot of them. If one of them goes down, then that's a large part of your infrastructure that is now not working. And while the data rates over geosynchronous connections are very high, the round-trip latencies are also high because they're in such high orbits. A mitigation for this is to use low Earth orbiting satellite constellations. These are satellites that are only on the order of 500 kilometers up, and they don't stay in one point in the sky. They're crossing the sky all the time. But if you have enough of them, then they can maintain connections, internet connections between points on Earth's surface by maintaining communication among themselves and switching the conversations as satellites rise in the east and set in the west. This enables you to have broad coverage areas and low latencies because they're very close to the Earth. The data rates are lower than for geosynchronous orbits. You need a lot more satellites because they only are visible for brief periods of time, and they're still expensive. The manufacture and launch of an Iridium satellite has, the last I checked, was on the order of $150 to $200 million. There's a lot of money involved in deploying these things. So an alternative would be use something that's emerged over the last decade, maybe a little bit less than that, a nano satellite, a tiny satellite. The most widely adopted model for these things is something called a CubeSat, which was developed at Cal Poly San Luis Obispo and Stanford several years ago, and was developed as a teaching tool for aerospace students. It's a satellite, you know, that thing on the table there, that's an entire satellite. It's a satellite that's 10 centimeters on a side. It's a cube. It weighs about a kilogram. And these things have been launched, and they go into orbit, and they have radios in them, and they can talk to Earth. They're a terrific teaching tool for students, but increasingly they're being appreciated as actual infrastructure that national space agencies, military, there are a number of applications. The rate of launch of these CubeSats is sort of growing exponentially over the last few years. If you had a constellation of these inexpensive nanosatellites in low Earth orbit, well, you could cover a large area of the Earth's surface, and you'd have no single point of failure because there's lots of satellites, and it'd be very inexpensive. So that sounds like a great idea, except that there's a catch there. There's always a catch. And that is that these nano satellites, these tiny communication satellites, the reason they're so inexpensive is that they're small and they're simple. There's not a lot to them. So the capability to do the conversation switching, the connection switching that you get from the Iridium satellites, it's very difficult to replicate that in the tiny form factor of these little satellites. Typically, they have very limited maneuverability on orbit. They normally only have a single radio, which is typically just a UHF radio. And so the connection switching across the cross-linked satellites that you get from a LEO constellation, you can't readily get from a constellation of these nano satellites. And so you can't reasonably expect a constellation of low-cost nanosatellites to be able to sustain even a small number, much less thousands or millions of continuous end-to-end internet connections. It's just not a good way to run the internet. All right, so how do we solve that catch? And what I will suggest here is that maintaining continuous end-to-end internet connections is not the only possible valuable network service to people using network applications on Earth. And that's kind of the basis for the rest of what I'm going to be talking about. DTN, which we've talked about a little bit already today, would enable a different model. At each moment, each of the satellites that's over some point on Earth, its radio would be in contact with some point directly below it. While the satellite and that ground station are in contact, data would flow between the satellite and the ground station, just between the satellite and the ground station. The satellite would function as a router, but it would function as a store and forward router. That is, the data sent from the ground to some other point in the network by way of the satellite would reach the satellite and stay there because the satellite's not connected to anything else. The satellite would hold the data in memory, and the satellite's physical movement along its orbital track would constitute essentially transmission of the data. When contact with the next ground station begins, network traffic exchange would resume with that ground station, and maybe some of the data that the satellite is holding in memory would go to the ground, maybe some would remain until a subsequent contact with another ground station. There might be some new contact added, and it's very much like the data mule model that Maria was talking about earlier today. The satellite functions as a high-speed data mule in the sky. And so because of the sort of circular nature of these orbits and because they sort of ring the planet, I've been calling this concept ring road. And I will go through a little demonstration here of a very crummy cartoon demonstration of how this kind of thing would work. The nomenclature on here, the dark red circles are what I refer to as hotspots. That is, these are nodes of this nanosat-based infrastructure that are connected to the internet and are also able to intercommunicate with the satellites. The satellites are the green guys that are termed couriers in this architecture. The dark blue guys are cold spots. That is, they're able to talk to the satellites, but they're not able to talk on the internet. They may have other devices connected to them over a local area network, but they're disconnected from the internet. The pale blue things are nodes that are neither connected to the internet nor to the satellites. They would use the cold spot to talk to the satellites. And the sort of pinkish pale red nodes here are things that are connected to the internet but not to the satellites. They would use the hotspots to be able to talk ultimately to the cold spots. So as an example of downloading a file using this infrastructure, let's take this picture here. We've got a user at do I have a, there, I do have a mouse, good. We have a user at node X here that has is requesting a file. This little blob is the file request, and here's the file that it wants to download. This guy wants to download this file, and he can't do it because he's on a local area network that's not connected to the internet. So what he does is request the file in this delay-tolerant constellation mechanism, and that file request is routed over the local area network to cold spot A, that is his cold spot, the one that connects him to the rest of the world. And it sits at cold spot A waiting for a satellite overflight. Well, fortunately, satellite number 2, courier number 2, is pretty close. So shortly thereafter, here comes satellite 2, and now the request can be uploaded from the cold spot to the satellite, and it goes into memory in the satellite, in the courier. And it just sits there waiting for contact with a hotspot. So the courier satellite continues on its path. For a while, it can't talk to anything at all, and now it reaches hotspot B. Because it's reached a hotspot, it can exchange data with a node that's connected to the internet. And that means that the request for the file can go to the hotspot and then immediately to node C, which owns the file traveling over the internet. The node at C says, oh, okay, I can provide that file, and determines that the earliest way to get the file to where it's supposed to go, which is by way of cold spot A back to X, is by way of courier 3 the next time it comes into contact with hotspot D. That's the next hotspot that's the next courier on the next hotspot. So to forward the file, what he does is forward the file not back to B, but rather to hotspot D, where it waits for not courier 2, but courier 3, which is further advanced, to approach. Courier 3 arrives, the hotspot uploads the file to Courier 3, and now it resides in the memory of Courier 3, it continues on its orbital path, it comes into contact with cold spot E, doesn't do anything with the file because E is not connected to X, continues holding it, still holding it, still holding it. Now it comes into contact with cold spot A, and so it's able to download it to A, which can immediately route it to client X. So what we have here is quite familiar request and delivery of a file between nodes that are not connected by the internet using satellites that are not conducting internet communication, they're conveying the data in a data mule sense. So what would this look like then to make this workable? I worked with a couple of guys at the Johns Hopkins University Applied Physics Laboratory to come up with parameters for the constellation that would make it usable. What we settled on was, first of all, the Courier satellites being in near circular low Earth orbits at inclination of about 50 degrees. As Maria was saying earlier, I think that's right. As we talked about in the ISS discussion, that covers about 95% of the Earth's population in that 50 north to 50 south range of latitudes. The altitude would be about 500 kilometers, and at that altitude, the radius of satellite visibility, that is, how much of the ground can see the satellite and the satellite can see at any moment, would be a little bit greater than 1,000 kilometers. So the diameter of the circle underneath the satellite at any time would be about 2,000 kilometers diameter. So the maximum separation of the satellites would be at the equator, which is about 40,000 kilometers. So if we had 10 orbital planes, each of the planes crosses the equator twice, and so each plane covers 4,000 kilometers of diameter of the equator. And so if you have 10 of those, then you've covered the entire equator. Each satellite would cross the equator twice per orbit. The coverage per satellite at the equator would be about 18 degrees of longitude. If you had 12 satellites per orbital plane, then that would be 18 degrees of latitude as well. But I'm figuring here 15, so there's a little bit of overlap in the coverage. And so that would come to 150 spacecraft in all. And Vint has a question now. Sure.
I'm not sure about the math, but did you need 2,000 kilometer radius rather than diameter?
I meant, no, I've been confused by this myself a couple times, and I think this is right. It's 1,000 kilometers radius, 2,000 diameter, but because it crosses the equator twice, coming down here, it's covering 2,000, right? And up here, it's covering another 2,000, so that's 4,000 altogether. Okay, so 150 spacecraft. Satellites at 500 kilometers altitude travel at about 7.8 kilometers a second, which gives you an orbital period of about 90 minutes, which is 16 orbits per day. So any single satellite would be in view of any single ground station for a maximum of 256 seconds. That's satellite rise to satellite set. If we used S-band transceivers, which is shortwave essentially, in the satellites, I believe we can pretty readily get 230 kilobits per second. And so during that 256 seconds of contact, you could, from a ground station, from a cold spot or a hot spot, upload up to 7.4 megabytes in a single contact. There would be up to 20 contacts of that maximum length per orbit. So you could upload almost 150 megabytes per satellite per orbit. And so about 2.4 gigabytes per satellite per day could be inserted into the network. So for 150 satellites, that comes to about 360 gigabytes inserted into the network per day, which is about 4 megabytes per second, 32 megabits a second. Now, that's not really fast compared to the internet, and which is not a big surprise because we're using quite slow radios. And it actually wouldn't be that fast, because you figure that 50 north to 50 south latitude, a lot of the time you're over the ocean, and there might not be anything listening. There might not be anything there. So you might be wasting some of that opportunity to upload data. So what I've said here is let's assume that there's something in the ocean from time to time, but not all that much. And so just divide it by 2 and figure roughly 16 megabits per second of traffic on a continuous basis into the network. At that rate, well, coming back to the cost of deployment, CubeSats are really cheap. You actually can go to a company called Pumpkin on the internet, and you can buy a CubeSat chassis for like $4,000. You can. There's a company called Tyvak in San Luis Obispo will sell you an entire the whole CubeSat ready to fly, except for instruments, for I believe something like $45,000. So we're estimating here an assembly cost of $100,000 to allow for maybe it's a 2-unit instead of a 1-unit device. Maybe there's an expensive radio. It's a rough estimate, and it could easily be off by 50% either way. But working with that number, we came up with a total satellite assembly cost of about $15 million. We estimated that the cost to launch 3 CubeSats would be about $200,000 for 3. So that'd be 50 of those. That's about $10 million to launch 150 CubeSats. And that price may actually be coming down because there's a growing commercial spaceflight market, things like Virgin Galactic, Sierra Nevada, SpaceX, where they really are seeking payloads to put into orbit. I think the trend in launch costs for these things is definitely downward. Then the other part is ground stations. Assuming about 20 contacts per orbit, 150 satellites, you need 3,000 base stations to occupy all of those contacts. But again, because it's only half the Earth's surface, you only really are having half of those, let's say. So let's say 1,500 base stations. The base station just needs to run the protocols and a shortwave radio, essentially. So laptops, if you buy them in bulk, they can be pretty cheap. So I'm guessing here that the base station would be something like $2,000 for every hotspot and cold spot. So the total base station cost of the network, I'm guessing here, is on the order of $3 million. Now suppose that the network lifetime is 5 years. Suppose we can keep these satellites going for 5 years, and just picking a number out of the air, let's say it costs $1 million a year to operate the network. People that are monitoring the network and updating routing tables and that sort of thing. In that case, adding it all up, the total lifetime cost of the network is 15 plus 10 plus 3 plus 5, $33 million. At 16 megabits a second, the total lifetime traffic over 5 years would be about 300 terabytes. And so that comes to a mean cost of transmission would be about 11 cents per megabyte. In contrast, if you go to the published price lists for communication using low Earth constellations that are available now, Iridium, I've seen prices as low as $7.41 per megabyte. Inmarsat, the BGAN Inmarsat service, $6.49 per megabyte. Thuraya, GMPRS Nova service, $5 a megabyte, which is a couple of orders of magnitude higher. And the thing that Mike was alluding to earlier, a couple of weeks ago I was talking with somebody whose name, of course, I forget because I'm very old. The invented Java programming language. What's Gosling? James Gosling. Thank you. James, who was speaking at JPL. He works now for a company called Liquid Robotics, and they make robotic surfboards that do science in the middle of the ocean. Their communication model is they're in the middle of nowhere. They have no option but to talk with through Iridium, and they are fairly heavy Iridium users. And what he told me is, $7 a megabyte? No way. We pay $1 per kilobyte. $1 a kilobyte to communicate from the middle of the ocean over Iridium. So I think 11 cents a megabyte is actually like an attractive alternative, and in fact I believe we could do a lot better than that, because the total capacity of the network really is limited by the data rates on the radios and the amount of storage and processing power on the satellite. So storage and processing power, they're becoming cheaper pretty much all the time, and we are now coming to the point where C-band or Ku-band radios are going to be available even in form factors as small as these CubeSats. So I think you can make a strong case that very inexpensive network service through this constellation is very feasible without any kind of miraculous scientific breakthrough. So I think it's well within technological plausibility right now. It doesn't matter in a sense, because the higher data rate is not going to solve the end-to-end round-trip time problem. The satellites only travel so fast. The latency and communication between the satellites and the ground stations is negligible because they're only 500 kilometers up. But the round-trip latency in the network could be pretty bad, right? It's going to be extremely variable and could be very high. And here's an example of that. Suppose you've got a subscriber on Seram Island in Indonesia, and suppose the preceding hotspot on the orbital track that the satellite follows is Manado, which is 800 kilometers away, and maybe the next hotspot is Darwin, 1,200 kilometers away. Okay, so a round trip, the picture that I was showing before, a round trip data exchange over that scenario would take 154 seconds of travel time from Seram to Darwin before it can load the data into the internet, and 103 seconds from Manado back to Seram on the return. The part that's on the internet, yeah, that's negligible, but the satellite takes some time to move. So you've got a total round trip time of 4.3 minutes. Okay, so can a network be usable when the round trip time is 5 minutes? And I think it's a fair question. I think it's a question that's really the main point of what I wanted to talk about today. Well, DTN was originally devised for automated network communication in spaceflight missions, where the round trip time between Earth and Mars can vary between 8 and 40 minutes. So for spacecraft operations, well, that's an application that clearly you have no choice. If you're going to do it at all, it's going to take that long. The network has to be acceptable, or else you don't have a network, you don't have communication, you might as well just stay here. So, and that's why we called it delay-tolerant networking, because the networking would work over extremely long signal propagation delays or other round-trip delays caused by whatever, including interruptions in connectivity. And clearly some network applications are completely stupid. You know, it would be useless to try to do Skype over an 8-minute round-trip time. It would not be fun. It would not make any sense. Teleconferencing, Telnet, SSH, there are lots of things that we can think of. But I will suggest that there aren't that many. There are plenty of things that we can think of, but not all of them. There are plenty of applications that we use all the time that I will suggest are innately delay-tolerant applications, that a round-trip time of 4 minutes, 10 minutes, 30 minutes is not necessarily disabling to the application. Email, which was actually one of the models for DTN thinking right at the beginning, it's nice when you can get a response email within a couple of minutes, but you don't really expect it. What you expect is to send an email and you hope to hear something back from this person the next time they pick up email, which might be in an hour and a half. News feeds, streaming news, streaming media, real-time or just blogs, weather advisories, crop reports, anything that is a one-way transmission of data. There's no need for conversational network capacity to do that. It's just fine to get that information when it arrives. And maybe a little bit less obviously, archiving, backups, documentation of things, taking photos of misbehavior at a demonstration and loading them to an archival photo archive somewhere. Anything where the communication is where it's more important for the communication to be reliable and secure than that it be timely is perfectly delay-tolerant application. And I think it doesn't stop there. Things like warning signals, distress signals, disaster relief, well, you really want those things to go through as quickly as they can. And if you've got high-speed connected media to issue those things, terrific. If you don't, well, then having them get through eventually is better than having them not get through at all. So I think these two are examples where 8 minutes in delay in getting a cry for help out is a lot better than 2 days or never. And even beyond that, it seems to me that if you look at a lot of social networking applications, they're not really necessarily conversational applications either. You post something on Facebook and you want everybody to see it, but they don't have to see it right now. You're not waiting for them to comment on it right now necessarily. If they see it in 3 minutes, that's not necessarily a problem. File transfer, media download. If you're downloading a movie, well, if you started a movie download and it took 4 minutes and you went out and had a glass of milk while that was happening, well, that would not necessarily be a big problem. And then a further class of applications that I think is even maybe less obvious is e-commerce applications, electronic commerce, banking, shopping, things like that. And what I'll propose here is that taking a step back and thinking from 45 years ago, anything that we used to do by mail that succeeded, and slowly, but succeeded when we were doing it by mail 45 years ago, you could do in a DTN-based network with 8-second round-trip times, and that would be a lot better than when it was a 4-day round-trip time 45 years ago. It doesn't have to be conversational. It still can work. Merchandise. We used to buy merchandise by mail order. The catalogs came in the mail. We essentially can do the same thing with Amazon right now, but suppose the catalogs arrived over time and maybe at night, and you browse the catalog in the day after it happened. You don't necessarily have to be able to be interactive with a catalog that is at a remote location. It'd be a lot better to be interactive with a catalog that had been downloaded locally to your machine. Bank statements, all of your banking information. Well, the bank could stream that stuff to you overnight, and when you go to balance your checkbook or whatever, as long as the information is current, and it doesn't change that fast, it's much better for it to be residing locally in your machine so that you're not sending queries into the bank's servers and having it go into the ether and nothing happens for 15 seconds, and then you say, oh, well, it must have gotten lost, and you hit the button again, and it goes the second time. In every case, the applications that are on a high latency network can provide, I believe, the same functionality way more quickly than with mail, and much more powerfully, because now they can be accompanied by graphics and automation, and the same functionality and really more securely. The pictorial sort of notion of this that I've been working with is something where imagine that businesses, banks, they have branch offices. There are banks that have branch offices. Well, suppose the bank, in addition to having branch offices, has twig offices. They're really small branches, and the twigs are downloaded to all their individual depositors, account holders' machines. So the twigs are full implementations of the bank software that are residing on customer subscriber machines rather than on the remote server. So the interaction of the customer with that information is immediate, it's very secure, it's not subject to delay or loss over the network, and the small fraction of interactions that actually require coordination with the central database of the server can all happen while the user has said, oh yeah, do that, and walking away. So sort of in that light, I'd like to offer this perspective on using networks. And it's that our concept of how to use a network ultimately derives from what I understand is the origin of the internet, which was modulation, demodulation of data over telephone lines. We expect the network to operate like a telephone, only more. And a high latency network breaks that expectation. It doesn't operate like a telephone anymore. But communication that is non-telephonic, it's not that there's anything wrong with it. It's been around for a long time. It's not necessarily inconvenient. It's not necessarily inefficient. For many communication applications, I will suggest that telephony really is overkill. You don't need it. And in some cases, and I think a pretty good example would be things like the Affordable Care Act, and people have been having all these troubles getting through to the servers to get into systems. Wouldn't it be better to just download that stuff to people's individual computers and then operate locally? And when you finally make a decision, you say, here's the little bit of stuff that I really want to have happen. Well, now send that off. And that can happen asynchronously from the point of view of the user. The user satisfaction, I think, would be actually a great deal higher. Oops. I don't know. Okay. Try that. Okay. And from that perspective, this is a diagram I've been sort of thinking about for a long time, that over time, communication sort of has two different, completely different flavors. There's conversational, synchronous communication. There's epistolary, asynchronous communication. They're both completely valid and extremely valuable, and they're complementary and have been from the dawn of humanity. This timeline, well, yeah, we started their initial communication. There wasn't much beyond speech, and then gesturing, right? Smoke, flashing mirrors, and then a huge technological innovation, writing. And suddenly, you could communicate with somebody who was not next to you because you could write something and hand the thing that you wrote to somebody who could carry it 2 miles or 200 miles to whoever it is that you're sending it to. Domesticating the horse, another huge technological breakthrough that made communication, epistolary communication, much faster. Ships, now you could traverse really long distances. Roads, real road building, which happened actually quite a long time after shipbuilding. Another tremendous technological innovation. Horses moved a lot faster over roads than over open country. And the railroad, another leap forward. But then, finally, a leap forward in conversational, synchronous communication in 1833 or so, the invention of the telegraph. And suddenly, the distance annihilation that you could get only from written communications, you could now get in a conversational way. The telephone was an extension of that. Radio, and things like communication satellites and the internet all derive from that. But as distance increases even further, now that we're pushing into space, suddenly the conversational model, again, cannot handle the full range of everything we do. And I think that's where DTN comes in. The pendulum swings back and forth. We need both styles of communication. And I think that a lot of the things that we do on the internet right now would be perfectly fine in a delay-tolerant network along the lines of the infrastructure I've been talking about. So a couple of quick caveats. The core implementation, the core protocol implementations for DTN I think are pretty mature. We're using them on space station, as we were hearing earlier. There's still some supporting software that's needed. You need something to do the route computation in that rather complex topology. You still need network management protocols and tools, and they need to be able to scale up to what could be quite a large network, right? 150 satellites, 3,000 ground stations. There's a lot of network there, and that's That's assuming you don't make it any bigger. And security. I think security is a huge issue. Fortunately, I believe the bundle security protocol and the security innovations that have been developed for delay-tolerant networking are actually pretty strong. I think, and we have those implemented already. There is still a need, as Fred was discussing earlier, we still need a scalable key distribution system, but I think that's also in grasp. The real issue, I think, here is where does the funding come from to build this? Because there is not yet a general perception that anybody can make any money from it. When I first had this idea, I thought, well, this is great. It won't make any money, but it'd be great for providing emergency communications to places that are devastated by earthquakes. It'd be great for communication to underserved areas like refugee camps. As I thought about it some more, I think that a lot of these applications that I have recently come to think are in fact delay tolerant applications, maybe motivate a commercial argument for building an infrastructure like this, and that'd be great if something like that happened. In the meantime, I think the idea has a lot of merit. The concept of DTN on satellites in low Earth orbit, as we discussed earlier, is well proven. And I think the concept has some pretty clear advantages as an adjunct to the way the internet works today. It surmounts geographical obstacles. It's not disabled by earthquakes, floods, fires. It's actually difficult to disable intentionally. It's difficult to shoot down a satellite, especially a satellite that's this big. There's a low barrier to entry in building the infrastructure, a low operating cost over time, and it would make it possible to offer internet-like service to a vastly greater fraction of the human population than we can offer right now. It would be a high latency network, and for some applications it would evidently be unsuitable. But for a lot of applications, I believe it would work as well as the internet, and in some cases even better. And that's the conclusion of my presentation. Thank you very much.
So that's pretty breathless. One question I have is whether we should consider building a bunch of applications that are DTN based and run them over the internet, so that when you finally get this system up and running, we won't know the difference. And that, this has some advantages. Not all applications that would work on the internet will work over the delay tolerant portion, but those things that are delay tolerant in the application sense wouldn't know the difference, and that's very advantageous.
So there's a cost to modifying existing applications to do that, and I think it'd be great to do that in concept. It's not clear to me yet what the business case is for it, and we have to have a business case for somebody to do it. I will say that as a transitional alternative, what we have looked at, and it's been shown to work, is running IP over DTN. It's bizarre, but what you can do is you can use the TUN-TAP interface at the bottom of the IP stack, and insert the bundle protocol in such a way that it looks like Ethernet and acts like Ethernet as far as IP is concerned. But it's a delay tolerant Ethernet. And once you've done that, well, any delay tolerant internet application automatically can take advantage of that. It's just that non-delay tolerant internet applications wouldn't work over so well. But as a way of insinuating DTN technology into the networks, that is, talking with the telecoms and saying we would like to have some bandwidth to run this stuff alongside the IP traffic. Well, I think that it's a pathway to having capability in place that then you could have applications that are native DTN applications have something to run over.
I'd like to add to that. A perfect example on ISS is that the crew has live email syncs to the Outlook server on the ground. Flight director a couple weeks ago 10 megabyte file to a crew member on an email, they'd try to create a TCP correction and crash Outlook. If we were able to DTN Outlook, we would be not having these issues with Outlook on the space station. This is one example.
Wait a minute.
My Bogon detector just went off. If you had put TCP over IP, or email on top of TCP over IP over DTN, if the TCP is still there, it's going to time out. So that's not going to work. So,
Yeah, but anything that's UDP based you'd be able to.
Okay, this is starting to get more complicated.
Yeah, it is. Yeah, you should see how the stacks look. It's pretty comical.
Yeah, Scott, that's a very good presentation. David Brin here. I just wanted to mention a couple of things and then ask a question. One is that orbital planes are not as simple as perhaps you implied.
Let me clarify by saying I'm a software developer. I'm not an aerospace engineer, so it's entirely possible that I got a bunch of this wrong.
Well, inserting, for instance, replacement CubeSats into existing orbital planes where these things, for one thing, you get precession of nodes, and they're all going to be separating in every which direction, like a bunch of scattering.
You need some sort of motive power on the satellites to be able to.
No, what you need is you may need twice as many, and in any event, a large number of your satellites are going to be dispersed not by dedicated launches, but by parasitic riding on other people's launches. So it's going to have to be very opportunistic.
Right, they're going to be where they are.
But that's also going to reduce your costs because they can be riding inside the fairings of other. That's what CubeSats do a lot. And of course, you're going to have some provisions for deorbiting them. And you can do that with electrodynamic tethers and things like that.
My understanding is that at 500 kilometers, they're going to deorbit within 5 years, sort of by themselves. The orbit's going to decay, and they're small enough they're going to burn up.
Yeah, but the movie Gravity has sensitized us to this thing. In any event, I just wanted to ask you, are you inspired to consider lasers that we discussed earlier?
Oh, sure.
And that would certainly make this into a very, very big deal, and they're compact, as we've seen. The other possibility is uplinking via ring road, but then getting your downlink information via the big satellites like Viasat.
Sure, that's
that way you change the whole economics of the thing, the whole latency thing, because it's the uplink that's the real problem, I believe. But you can set up a dish and receive stuff from Viasat. You can receive the files that you've ordered.
Yeah.
So
that's a very interesting concept. Sure.
Yeah.
And the one other thing on the optical, I think that actually would be terrific. My understanding is that JPL at least is developing something that would be small enough to fit on a CubeSat that would be an optical transmission device that doesn't exist yet. So I didn't include it because I can't cost it, but it's definitely coming.
This is Fred Templin from Boeing. To your point earlier about what the business model for this would be, I might want to consider the possibility that there might not be just one of these, but many of these.
Sure.
Special purpose for the airline industry, for example, or special purpose for government needs. Militaries, you can think of many different applications where they might want to have their own ring road that's kept separate from, for example, the public ring road.
And you could, I believe you could easily imagine sort of virtual ring roads within maybe a very large single population of satellites, and there might be possibly multiple coexisting nodes on a single satellite that are participating in separate private networks and drawing boundaries among them by the security protocols.
Right.
Sure.
Okay, thanks.
Einer Fulsang from Ames down the road. You should really come see us. We have a CubeSat system integration shop that would love to talk to you.
Guys, yeah.
Okay. In particular, what you showed was a picture of a 1U CubeSat.
That's right.
Almost nobody launches those anymore except universities who want to wow the grad students. Typically today they propose 2U, 3U, 4U, 6U because you can cluster these things together. You only need one attitude control system and that leaves the rest of your space for payload. So you might want to ask yourself, what can I do with that extra payload? Well, one thing I could do is I could have a more powerful transmitter to get my data up and down. I could store more data. But another thing you might want to consider, and this is not my field, so I'm just kind of bloviating here, but a lateral transfer. In other words, if I've got a sufficient population in my ring, and it uploads on one instead of having to wait until I get to a good download spot, pass it to my neighbor, and then have him pass it and pass it and pass it. You could do this very, very fast and almost conquer the the latency problem. But what I do like, though, is the fact that you've actually scaled a viable proof of principle concept that could actually make money. That's unusual. It could solve Maria's problem. Okay? And now, if your market picks up, if you prove that there's a market there in this manner, you can then start putting up more satellites or putting up bigger satellites and start to attract more and more. You've got a growth model.
Thanks. I think that's right. Yeah. Pardon me? Oh. Yeah. Just as an aside, sorry, just one moment. I commend to everybody the Liquid Robotics website. These things are the coolest things you ever saw in your life. They're these ocean-going robots that are like large, thick surfboards that are completely self-propelled using no fuel. They're completely propelled through to any point on the surface of Earth using just wave motion. I mean, it's a gorgeous, elegant design.
First thing I wanted to say is this is absolutely tremendous, just a wonderful, wonderful thing. And a lot of it is because I think it's just like rural electrification. There's a lot of underserved population in the United States. And unfortunately, internet access and network access is becoming a real divide. Everybody needs it, and if you don't have it, you're out of the conversation. So it's very, very important. Having said that, I was trying to do the business around what you said, because as the gentleman said, I think there's obviously a money-making proposition here. And you know what? I mean, you just go down the road here. I mean, there's like row after row of venture capitalists. But what they're going to want to see is I mean, if you want, I'd be happy. I've done zillions of venture presentations, unfortunately. So I'd be happy to talk to you.
Let me just interject here. I've like in earlier younger days, I've done like the VC kind of thing and tried to start things. And I recognize that that's not me. I'm actually not very good at that. But if somebody's interested in doing this, I'm very delighted to offer whatever technical support I can. I think this is the coolest thing going. I would love to work on this.
Yeah, you need somebody with business and time, and unfortunately, I'm overwhelmed. Otherwise, I think it's a tremendous idea. But somebody should really pick up on this.
I so agree. Any other questions? Oh, yes, please.
When you were quantifying your demand, you used mainly the network or capacity as your metric. Have you done any customer verification to see what the demand actually would be?
So the question is, when I was quantifying the demand, I was using network capacity as the metric, and has there been any quantification of the actual demand from the potential customer base? And I would say no. I haven't tried to do anything like that. I've assumed, and this may not be correct, but I've assumed that whatever bandwidth were made available this way would be consumed by some activity or other. At the least, people in the middle of Pango Pango would be downloading Tom Cruise movies. I'm sure that the bandwidth would get used. The things that I think are real constraining factors are how much it's going to cost, how much people can afford, and if you don't price it so high that the the people who recognize the value of the service can't afford it, then I believe it would be fully subscribed. Any other questions? Oh, sorry.
Yeah, I work in the field a lot with projects, not quite like the reindeer, but we're in the field a lot with dolphins and whales, mostly photographing the babies after they've been born. And I'm usually on uninhabited islands where we have no communication at all, but this is more of the delayed material that we would get out. But the real-time material we need in case there's an emergency, because we see a lot more sharks than we do whales. And I'm just thinking that some of the outreach that we have, as far as like we have about a 300 million viewership on one of our brands that we don't actually launch yet. But if we put it together with something that's needed and go to the entertainment industry to talk about what you're doing in the development with a good story, it might be something that could lock in with the lady who's doing there. Maybe we could talk a little bit about it.
In a sense, I can imagine sort of this concept, even without the crosslink sort of idea that was mentioned earlier. Just the vertical up and down and carried thing as a high bandwidth, mass data movement at very low cost mechanism that would be supplemented by a conversational mechanism that Iridium gives you, so that if you have an emergency, you don't mind spending $1 a kilobyte for immediate phone call connectivity, and for a lot of other activity, the fact that it takes a long time just doesn't bother you, and on that basis, I think the sort of model you're talking about, that's certainly something to consider. Your sharks and whales thing is the point is certainly well taken, and I think there's room for both.
Yeah, particularly one particular production company I have in mind that we're talking to right now. It's on the IMAC